In this video, we're going to look at a constraint optimization problem where we want to find the points on a surface that are closest to the origin, but then we're also going to try to classify the critical numbers using some form of Hessian criteria. Now, the Hessian criteria for constraint optimization problems is going to get weird. So it's kind of summarized to the right here, but I think we'll have an easier time talking about what this is once we have some numbers to play with. So let's go ahead and start by solving the constraint optimization problem. So we have a function we're trying to optimize, which is x squared plus y squared plus z squared. Just because I'm eventually going to say Hessian, I'm going to write the gradient as df, just, because. So I'll have 2x, 2y. If I'm writing it as a matrix, let's write it as a matrix. And then I have my constraint equation, which is going to be x. So this is distance squared. That's always what we like to use. This is going to be x squared plus y minus z. And the gradient, or the derivative, matrix of partial derivatives for g is going to be 2x, 1, negative 1. So we get this nice system of equations. We're going to have 2x, using this Lagrange multiplier idea, we're going to have 2x equals lambda 2x. We're going to have 2y equals lambda. We're going to have 2z equals negative lambda. We're going to have x plus y, or x squared plus y minus z equals 3. That's our system of equations. Now, we know two things right off the bat. By looking at the second and third equations, we know that y equals negative z. And we also know that either x equals 0 or lambda equals 1. And both will give us interesting things. So let's go ahead and find out what each of those are. So if x equals 0, we're going to have the equation y minus z equals 3 from our bottom equation. But y equals negative z, so this is just y plus y equals 3. We've got y equals 3 halves, z equals negative 3 halves. So that would be one solution. Of course, x is also equaling 0. And with what we're about to do, we're also going to want to know what lambda ended up being. So we should find what lambda is. You can maybe use this equation here and see that lambda equals 3. So that's one set of equations. Otherwise, lambda equals 1. If lambda equals 1, then we know that y has to equal 1/2 from our second equation. Z has to equal negative 1/2 from our third equation. And that leaves us with x squared plus 1/2 plus negative 1/2 equals 3, or actually minus negative 1/2. From our fourth equation, that's going to end up being that x squared equals 2, or x equals plus or minus square root of 2. In both of these cases, we also have that lambda equals 1. So we have lambda equals 1, x equals plus or minus square root of 2, y equals 1/2, and z equals negative 1/2. Okay, so we found our critical points, and now we want to use some form of Hessian criteria. You're going to have a block of zeros in the upper right corner. This is going to be n minus k zeros. So what are n and k? N is the number of variables, and k is the number of constraints. So in this case, we have n equals 3 and k equals 1, I'm sorry, that number is not going to be n minus k. That number is just going to be k. So you're going to have a block, a k by k block of zeros. And then here, you're going to have negative the matrix of partial derivatives of g. I'm writing g as a vector valued function because sometimes we have more than one constraint, in which case we kind of want a like stack of gradients, which is our matrix of partial derivatives. And that's why I wrote it this way. But you'll note that we have a special criteria that the upper corner of our matrix of partial derivatives for g should have a non-zero determinant. That's actually going to be a problem here, but we'll come back to that soon. Here we're going to have negative d of g transpose, so we'll just flip it. And then the rest of this is going to be the Hessian of f minus the Hessian. So we take the Hessian of f minus lambda 1 times the Hessian of g1 minus lambda 2, the Hessian of g2, etc., etc. In this case, we only have one constraint, so we don't need to do a whole bunch of extra stuff. So that's what this weird Hessian is going to look like. Let's scroll down a little bit. We know f was x squared plus y squared plus z squared. G was x squared plus y minus z. The matrix of partial derivatives of g was 2x plus 1, 2x 1 negative 1. Now, we might have a problem if this upper corner, which is basically the biggest square matrix we can fit in it, if this has a determinant of 0, we have a problem. And it turns out we do. Because you'll notice, if we scroll up, one of our critical points did in fact have x equals 0. So what we need to do is reorder variables. So we're going to reorder variables so that this doesn't happen. So maybe something like now we're going to live in a universe where y comes before x comes before z. We don't always have to do this switch, and actually in the text, one of the examples has this exact problem and just doesn't address it, so maybe that's an issue, who knows. But let's go ahead and do the switch here just so we can be super extra careful. So now we kind of need to think about our matrix of partial derivatives a little bit different. So df isn't actually going, and we're going to change both df and dg a little bit. Now we're going to live in a universe where y comes before x, so we're going to start with the partial in respect to y, and the partial in respect to x, then the partial in respect to z. Then dg is going to be, it's going to be partial in respect to y is 1, partial in respect to x is 2x, partial in respect to to z is negative 1. And thankfully, this is never 0. So we're all good there. Okay, so let's go ahead and start setting up our Hessian. Well, actually we need to calculate two other things. We need to calculate the Hessian of f in this strange world. So we'll have 2y with the derivative in respect to y. So here we'll have gradient of this. That's going to be 2, 0, 0. Then gradient of this. Gradient in respect to y is going to be 0, and x is going to be 2. In respect to z is going to be 0. In respect to, and then lastly here. Hopefully that's not too surprising. Then we also want to look at the Hessian of g in this same backwards world. So we're going to have the derivative of 1 in respect to, anything is 0, 0, 0, so that's nice and boring. Then we're going to have the derivative of 2x in respect to y is 0, in respect to x is 2, so we'll have a 2 right there. And then that's going to be 0, more zeros. And if you remember the different pieces that we're going to have of our matrix, we're also going to need the Hessian of f minus lambda times the Hessian of g. So if we do that, we're going to have the Hessian of f minus lambda times the Hessian of g. It's going to equal 2, 0, 0, 0, 2 minus lambda times 2. Or you could say 2 lambda if you really wanted to. Zero, and then 0, 0, 2. And now we can put together our big Hessian matrix. So this is going to be an n plus k by n plus k matrix, where n equals 3, k equals 1. And so we're going to have a block of k by k zeros. That's just going to be 1, 0. Then we're going to have the negative the negative matrix of partial derivatives for g. So that's going to be negative 1, negative 2x, 1. We'll have the same thing going down in the transpose here. And then we're going to have this Hessian of f minus lambda times Hessian of g filling in here. So we'll have 2, 0, 0, 0, 2 minus 2 lambda, 0, 0, 0, 2. So we have that. That is going to be very important. Next, we want to look at a sequence of partials, or sequence of minors, sort of. We're going to look at the sequence, look at negative 1 to the k, d of I, where di is the determinant of the I by I matrix, upper I by A matrix in corner of HL. And we're going to look at what pattern this has from 2k plus 1 to n. Or to k plus n, actually, not just n. So what's that going to look like? Well, first we'll have negative 1 to, in this case, k is 1, so this will be negative 1 to 3 times the determinant of the upper 3 by 3 matrix. I put that wrong thing here. That exponent should just be k, and k in this case is 1. But we are going to look at the upper 3 by 3 matrix, so we are looking at D3 here. So I guess I'll write that down just for clarification. So we're looking at negative 1 to the 1, or to the k, times D3, which is negative 1 times the determinant of 0, negative 1, negative 2x, negative 1 to 0, negative 2x, 0, 2 minus lambda 2. That determinant is, if you do lots of fun math, you will get that, well, di, once you do all the stuff, is going to end up being 8x squared minus 2 lambda plus 2. I would honestly recommend using something like Symbolab to take care of these determinant calculations, because it's going to get worse from here, because, for example, we then want to look at a negative 1 to the 1 times d4, which will be -1 times the determinant of the whole Hessian. 0, -1, -2x, 1, -1, 2, 0, 0, -2x, 0, 2 minus 2 lambda, 0, finally 1, 0, 0, 2. And that's just gross. So I would go ahead and use the some tool to take the determinant of that. You can do it without, but I would suggest it. And you'll end up getting something like 16, once you multiply by -1 as well, 16x squared minus 8 lambda plus 8. So these are going to be, this is the sequence you're looking at. And we're wondering, kind of like what we did with the Hessian, is this positive, 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 etc. If it's that, then it's a minimum. If it's negative, then positive, then negative, then positive, etc., then this is a maximum. And otherwise, it is a saddle point. So we're then going to test our points. We had the points 0, 3 halves, -3 halves, and plus or minus square root of 2, 1/2, -1/2, if I recall correctly. Let's go ahead and double check that just to make sure. Yeah. Okay, and I'm going to scroll down slightly more so that we have room to do this. And we also needed the lambda values. This had a lambda of 3. This had a lambda value of 1. And let's go ahead and see what we get. So for 0, 3 halves, -3 halves, lambda equals 3. This sequence is going to look like -1 to the 1 times d3. It's going to equal 0 minus 6 plus 2. So that's going to be -4. So it's definitely not a minimum. Might be something else. And then we're going to get, for the next one, -1, 1 dot d4. That's going to be 0 minus 24 plus 8. So that's going to be -16. Which tells us this is a saddle point. And if you look at the picture of what's going on here, this is a point that is fairly close to the origin, but it's not quite as close as the other two. Which means that as you move towards those other points, it's going to get closer. But as you move in other directions, you're moving away from the origin. So it makes sense that this would be a saddle point. We can do plus or minus square root of 2, 1/2, -1/2, all in one go. The reason why that's relatively easy to do in one go is because x is being squared anyways in both of these cases. So it really only matters what x squared is, which is the same in either of those. So we'll have -1 to the 1 times d3 equals, that's going to be 16 minus 2 plus 2 equals 16. So it might be a minimum. It's going to be a minimum. And let's go ahead and check the other one. We'll have -1 times d4. That's going to equal 32 minus 8 plus 8 equals 32. In fact, yes, we did get plus, plus. Back here we got minus, minus. So that led to saddle point. But we have plus, plus here. That means we have a local minimum. In fact, if you go ahead and check it out, the distance here is going to be, should be square root of 5 halves, or square root of 5 over, I think it's, yeah, just square root of 5 over 2. Don't quote me on that, but I'm pretty sure that's right. Whereas this has a distance of square root of 9 over 2. So a little further away. Because yeah, you get 9/4 plus 9/4 is 9 halves. That's the distance squared, and then yeah. So we actually see that this is a local minimum, and it's, you know, fairly clear to see that this is also a global minimum. Justifying that is easier said than done, but we clearly don't have anything like, there's no reason to believe there's an infinite number of points super duper close to the origin. So it's relatively easy to believe that this local minimum is actually a global minimum. But anyhow, that shows you how to use the Hessian criteria for these Lagrange multiplier problems. Obviously, there's a lot of work to do, but as long as you break down that Hessian into smaller pieces, it's not too scary.